let's start this. And so we have Suhail computers help you with gradient descent. So at Vector Institute Toronto, he recently completed his PhD from TIFR, and his research interests are complexity theory, query complexity, and communication complexity, etc. Okay, so over to you, Suhail. Thanks a lot.
Thanks, Nitin. So as you mentioned, this is all just about gradient descent and whether now that we have quantum computers better than we could do classically. And the answer is no, as my title says here. But it's still going to be an interesting journey, even though I've spoiled it. As you said, I am now a postdoc at Vector Institute, but this work was done when I was a research intern at Microsoft in Bangalore. And these are my co-authors, Ankit Garg, Robin Kothari, and Praneeth Netrapalli. So to start with, we'll just see what gradient descent is. Although many of you might be familiar with it, it's worth going through. So it's a really old method. It was formalized back in 1847, and it was designed in order to find places where functions take small values. We're trying to minimize a function. And the method is really simple. You query the function at some point and we get some value. Then you also compute the gradient of the function, which is the direction in which the function value will increase. And you take a step in the opposite direction. So over here, we've taken a step in the opposite direction and the function value happened to decrease. And we just repeat this process over and over. And the hope is that as we continue doing this, our function value will decrease a lot, and that this would be an efficient way to actually find a minimum or a local minimum of a function. And it actually is quite magical, especially when you have high dimensions, which means that there are lots of variables, and you want to find the setting of the variables to which, say, some function, say the loss function of a neural network, for example. That's a great example. So a neural network has, like, every edge in it has some weight associated with it. So there are lots of parameters. And gradient descent is a nice way to find out what parameters should I set in order for the loss function to be minimized. And so it's actually used a lot in practice, even apart from neural networks, which are particularly good for gradient descent. Some programming languages now allow you to automate finding optimal parameters using gradient descent. So the first question is, how do you find, computing the function will assume that we can do that, because that's like the very basics. But how about computing the gradient? That's an important step in the gradient descent method. And it turns out that this is hard. So let's take a simple example to show this. And if my handwriting is too bad, if you can't read it, please let me know. So let's take a function of the form, say, f of x is x inner product v. So x is an n-dimensional vector, v is an n-dimensional vector, and we're just taking the inner product. So this is a plane, and if you're trying to find its gradient, well, the gradient at any point is just the vector v itself. So the gradient is equal to v. And let's assume that we've chosen v to be uniformly at random from the unit ball, say. Now, if you were actually computing the function, so say you you queried at some point x1, you found the value of f of x1. What this implies is that you've received the value of x1 inner product v. So you haven't learned the gradient, but you've learned one component of the gradient along the direction of x1. And there's a very important lemma which says that if you're in n dimensions, if v is completely random, then no matter what x1 you take, with high probability, x1 inner product v will be between 1 by root n and minus root n component of v. And to actually you can do the calculations, you will need square root of n queries in order to learn approximation. gradient of a very simple function. And even then, find same time, it turns out finding the gradient is actually easy. Now, in this formulation, we know how to compute. We're not just given f of x as a black box. So if you're given a set of steps on how to compute f of x, then you can also compute the gradient of f of x in around the same time as it took to compute f of x. It's like 6 times the amount of time taken to compute f of x. You can also compute the gradient. So in that sense, it's actually quite cheap to compute the gradient, and that's what makes gradient descent such a wonderful algorithm. It's actually cheap to do the whole way through. But what guarantees does gradient descent have? So it's nice, has some kind of magical performance, it's easy to do, but what mathematical guarantees can we give about gradient descent? That's the first part of this talk, where I'll talk about how gradient descent is, in a sense, an optimal algorithm for the task of first-order convex optimization. This is where gradient descent really shines. So what is first-order convex optimization? You're given a convex region B in which you're trying to optimize a function, and you're given access to a function f. And what I mean by access here is that you're given an oracle, you can query x, and it will return to you the value f of x and a gradient of f at the point x. And what we want to do is we want to find the minimizer of f. So B is the convex region. You're finding the x in B, which minimizes f of x. This question, unfortunately, is impossible because f might have small variations, and finding the exact minimum could be, it actually is impossible with a finite number of queries. But we'll relax this and we'll just say we want to find some point x prime in the region, which might not be the optimal, but it's at most epsilon more than the optimal. So this is the task of first order convex optimization. Unfortunately, even given this task, I can't tell you how many queries this will take. And the reason for that is best seen by example. Here are two functions. I've plotted them at some discretization of the grid. So red over here are the points that have a value that's at most epsilon more than the minimum. So outputting any of these would be a valid solution to the convex to our task. On the right side, I have a similar function, which is just like a maximum of 2 planes. And over here is the set of epsilon optimal points. But notice what happens if I take this diagram on the right and I scale it. So here, the right side is just the left side scaled by 3. So it's essentially the same function. When you're making a query here at some point, it's the same thing as making a query over here and just dividing it by 3. They're essentially the same function. Unfortunately, the task is not the same, because the task over here was to find one of these points, but the task over here is actually much harder. Because we've stretched the function, the set of points that are epsilon optimal on the right side are much smaller than the set of points that are epsilon optimal on the left side. So when we're phrasing this question of convex optimization, we also need to fix a maximum slope. But notice that if you're epsilon optimizing on, say, if you're epsilon optimizing this function on the left side, it's equivalent to epsilon by 3 optimizing the function on the right side, because it's just scaled by 3. So an epsilon by 3 optimal point, sorry, there should be a 3 epsilon optimal point. So 3 epsilon optimal point on this side would actually be the exact set of points corresponding to epsilon optimal on this side. Epsilon optimizing on the left side and 3 epsilon optimizing on the we notice is more general function. There is G Lipschitz in a ball of radius r divided by G and something similar with r, a function that has slope at most 1 in a ball of radius parameter has changed. So if we just focus on this task, where we know that the function is 1 Lipschitz and the wall is of radius 1, this is actually as general as the complete task. Now, yeah. Yes. Right? That is, so if you're using gradient descent, that's true. It will lead you faster towards the minima. But if you just think of it as a task in general, where you're just given access to a convex function, and we don't really know what algorithm we're using. No, actually, no. I think yes, it does have oracle access to the gradient. So it's true. So the gradient will take you to it'll take you on a steeper descent. So in the sense that if you were doing it on this function, and you're going from this point to this point, over here also the oracle will take you from the same point to the same point. It's just it's steeper on the right side because the function is steeper. Did that make sense? So the set of the points that you query are still going to be the same on the left and right side. It's just that their function values are now steeper on the right side. Was that, I mean, would you agree with that? Yes, right. So even if you're going steeper on this side, on the left side, you just needed to reach one of these points, right? On the right side, we have to reach a much smaller number of points. So even if it is moving at a more steep rate, on the left side, it's possible that you finally, say, reach a point over here. And on the right side, similarly, you would have reached a point over here. So the right side still is harder because the set of points has also decreased. I'm not sure if that was convincing, but yeah, I mean that's what happens. I can't think of a better way to phrase it, right? Yeah, the fact that you're just adding epsilon here, and this epsilon does not scale when we've scaled f, that's what makes the site harder. Is that okay? Yeah. Okay. All right. Now this, so the task is described. One small thing left to actually address is what exactly is a gradient. So in general, a gradient at some point x it can be represented by a plane passing through the point x comma f of x. And it has the property, at least for convex functions, that it stays completely below the curve of the function. So the blue curve here is the function, and the orange curve is the gradient. And there's a similar thing in higher dimensions on the left side. But one problem is that just because a function is convex, it doesn't mean that a gradient has to exist. For instance, at this point here, for functions which aren't differentiable, you can't find a single there's no unique gradient curve. And so we say that a vector is at x if and only if the plane defined by that gradient, by that subgradient, is always smaller than the function value. So this is And just to be technically correct, we should be dealing with subgradients. Right. So now I've actually completely described the task, and the obvious question that one would ask is, what algorithms are there to actually solve this task? In the case of a one-dimensional function, so x only ranges, say, between minus query in the middle and find out which direction the gradient move in the opposite direction. So we'll start off by moving in this direction, then we query at the midway point here, move in this direction, and we're basically doing a binary search in this one-dimensional space to find the smallest point. And within log of 1 over epsilon steps, we will reach epsilon close to the minimum. And since our functions are one Lipschitz, that means that you're actually epsilon close in terms of the function value as well. What about higher dimensions? So you have an n-dimensional function. There is a method that does something similar. It's called the center of gravity method. And it states that if you look at the center of gravity of a convex set and you take any plane passing through it, it will split your convex set into roughly equal volume pieces. The volumes on both sides will be a constant fraction of each other. And so this will also give us a similar performance. It's kind of still doing a binary search in an n-dimensional space. It's starting with the ball of radius 1. It's ending with, well, it's not actually ending with the ball of radius epsilon, but let's just ignore that for now. And it will take approximately n times log 1 over epsilon steps to actually decrease the volume till you know that you're epsilon optimal. So this is the center of gravity method. It's binary search, which means it must have really good performance. But the method we're more interested in is gradient descent. I won't mention why I call it projected right now, but subgradient descent because you're actually getting subgradients. And this is how it works. There's an optimal point x star. We don't know where that is. We are at some point x, and we do one step of gradient descent, which moves us in the opposite direction from a subgradient. Eta is some parameter over here, which we'll want to fix later on. But this is what one step looks like. We go from x to x prime, which is defined as x minus some factor of the subgradient. And what we're guaranteed by the very definition of a subgradient is this, that if we went along, so say this is the, so say we start at x and we move along the plane defined by the gradient, we move towards x star. Well, then what we know by the guarantee of a subgradient is that along the plane, the value of the plane, or say the height of the plane, must have decreased more than the function decreased. That's the only way that we'll always stay below the function curve, is if the plane is decreasing faster than the function. So what that means is the decrease that we experience along the plane is more than f of x minus f of x star, which is how much the function changes. And that's a really nice simple mathematical statement, mathematical guarantee that we have here, because it means that it tells us something about the inner product of this vector and this vector. And we'll want to use that somehow. And the way we use that is with the famous cosine law. The cosine law states that if you have a triangle with sides A, B, and C, then we can actually tell what the length of C is. C square is nothing but A square plus B square minus twice the inner product of A and B. And if we use that to find out what is our distance from x prime to x star, this is what we get. The distance from x prime to x star squared is at most a squared. Now, since our gradient is at most 1 in any direction, a squared is at most eta squared. B squared is the distance from x to x star. And the minus 2a inner product b that we have by this above formula, it means that we're at least subtracting this quantity. So we might be subtracting more. This left side might be larger than the right side, but we're at least subtracting this quantity. Right. So this is the guarantee that we have. Now, if we set eta to be equal to epsilon. Yeah, so let's just set it to be, not if we set it, we set it. Now if f of x minus f of x star is greater than or equal to epsilon, then this above expression has decreased by epsilon square. So we've added epsilon square and we've subtracted 2 times epsilon times epsilon. So this says that if x is not epsilon optimal, then we know for sure that we're actually decreasing by a significant amount, by epsilon square. So therefore, we're guaranteed that within 1 over epsilon square steps, you have to have reached an epsilon optimal point. And that's a proof that gradient descent only takes 1 by epsilon square steps to solve the task. If there are any questions here, I can take them. And feel free to interrupt me at any point. Cool. So these are the 2 major algorithms, and we'll see when exactly one is better than the other. So let's just fix some small value epsilon, and let's look at as the dimension increases, between 1 and 1 by epsilon square, the center of gravity method should be more efficient because its complexity is just n steps. Okay. And from 1 by epsilon square onward, projected subgradient descent will be more optimal because n is larger than 1 by epsilon square in this region. So here we have a dimension independent algorithm. It doesn't care about what your dimension is. Within 1 by epsilon square steps, it guarantees that you've completed the task. Now the obvious question is, are there other algorithms which actually do better than this? And that's what we'll see in this slide. So in the deterministic case, it's been known for like 4 decades now that there is a function class which has dimension 1 by epsilon square, and for which solving the task requires 1 by epsilon square queries. So this means that gradient descent is actually optimal in this whole region. And you could also show that center of gravity is optimal in this region as well. So the above 2 algorithms actually are the best algorithms. In the randomized case, it was known again that when your dimension was something like 1 by epsilon to the 20, that you do take 1 by epsilon square steps. So even here, it was known that gradient descent is the best dimension independent algorithm. You can't do better than 1 by epsilon square without bringing in some dependence on n. But much more recently, it was shown that even if your dimension is 1 by epsilon to the 4, gradient descent is still optimal from this point onwards. And what we show in our paper, one of the things we show, the smaller of the 2 results, is that even if your dimension is as small as 1 by epsilon square, you still have the same lower bound, omega 1 by epsilon square queries. And this is something that we'll actually see in this talk in a little bit. All right. So this actually isn't a big result because it was already known that gradient descent is optimal up to log factors. So there was a lower bound of 1 by epsilon square log 1 over epsilon, but we just removed that log factor and pushed it to 1 by epsilon square. And we'll actually see that lower bound right now. I'll skip this slide. Right.
Sorry, Suhail,
Yeah.
I have a question. From 1 over epsilon to the 4, it went to 1 over epsilon square times log 1 over epsilon, is it? And then...
No. So the lower bound, there was always known that from this point onwards, there's a lower bound of 1 by epsilon square log 1 over epsilon queries.
Oh, I see. On the queries, if the dimension is at least 1 over epsilon square.
Yeah.
I see.
So it's telling you already that gradient descent, as soon as you reach here, gradient descent takes over from center of gravity. And in fact, nothing can do better. Maybe a log factor better, but our result is saying no, even that log factor is not possible.
And below 1 over epsilon square in the dimensions, the center of gravity still remains the best.
It still remains the best even for randomized. Yes. So let's take a simple function to start with. Our function takes in an n-dimensional tuple, and it just returns the maximum dimension, the maximum value in any of these dimensions. This should be easy to analyze, so let's do that. In the unit ball, the minimum value that this will take should be -1 by square root n, and it'll take this value at the point which is all -1 by square root n. If you try to make the minimum any smaller than this, then x will no longer lie within the unit ball. And also if, say, if x was equal to, say, 1, 3, 0.1, then the minimum value over here is 0.1, and in fact E3 will be the subgradient at this point. So E3 will belong to the subgradients of f at x. And this is simple to see that if you increase along the direction of E3, then your function will increase. Otherwise, if you take any of the other directions, it's going to increase slower than that. Right. Yeah. So this is the base function. It has nice characteristics. Now we'll create a class of families from this base function. And we're going to do it by just flipping some of the axes. So it's still a maximum of the various coordinates, except some of them might have minus signs in front of them now. That's the only difference. So again, the minimum should still be -1 by square root n, and it should be at a similar point with just the axes flipped correspondingly. Let's set epsilon, the epsilon in the task, 0.9 by square root n. What this implies is that if x is epsilon optimal, notice that the minimum value it can take is -1 by square root n. So then if x is epsilon optimal, this implies that the value of f of x should be less than 0. In fact, it should be, say, it should be less than equal to -0.1 by square root n. And this is the fact that we'll use. So now let's analyze how this f works. Let's make some query. We don't know what the values of z are, and we're just going to be querying fz without knowing what the values of z is. And suppose that we made this query. So this query says that in the first coordinate, x1 is slightly positive, in x2 it's very slightly negative, in x3 it's really negative, and so on. If you want to know what the value is of f of x, I'm going to claim that the first bit that you check is the value of z3. If z3 happens to be negative, then we already know that the maximum over here is z3 x3, and none of these other values are going to matter at all. None of the other values of z matter. If z3 happens to be positive, then the next thing that we have to check is the value of z1. And suppose that that is positive, then we know that the value of f of x is just z1 times x1. Again, other values of z were completely irrelevant for this calculation. And let's assume that z was actually sampled uniformly at random. So now that we chose this query to make, with half probability, we knew that at z3 we could have already gotten a negative, and we would have gotten the value z3 x3. With half probability, it was good for us, and then we look at z1. So in general, around 2 bits of z are revealed per query, and it doesn't matter which query we choose. We will get on expectation only 2 bits of z per query. This is the main observation to make for this lower bound. So if you haven't made this observation, do let me know where you're confused. All right, so
could you explain? Sorry, could you explain how you're getting the probability half by?
Right. Okay. So I'm saying that Zi is. Okay. Yeah. So Z is uniformly sampled from 0, 1 to the n. And then we're given access.
Sorry, plus 1 minus 1 to the n.
Oh, yes, right. Yeah, from plus 1 minus 1 to the n. And we're given access to fz. We're given query access to fz. We don't know what that is. And we made some query. Suppose that this is the query that we made over here. Now, if it so happened that Z3 was actually equal to minus 1, then we would have found out the maximum, or say, fz of x would have been equal to Z3 x3, and we would have gotten 0 information about any of the other bits. So that's with half probability this will happen. And with half probability, it would have been plus 1, in which case we have to look at the next largest coordinate of x. And we would have to ask, okay, what if z1 is negative? If z1 is negative, then x1, z1 would have been negative, and then we would look at z4. But if z1 was positive, then we already know that f of x is basically z1, x1. Right?
Okay,
so
okay.
with half probability, we would have been stuck at Z3. With half probability, we would have passed from Z3 and seen Z1 with 1/4 probability. And with 1/8 probability, we would have gone to Z4. And
All right, thanks.
hey, thanks for the question. So on average, on expectation, we reveal 2 bits of Z per query. And to actually find an epsilon optimal point, we know that the value of f has to be negative. And if the value of f has to be negative, that means that z1, x1 has to be negative, z2, x2 has to be negative, and so on. Each of them has to be negative. So if you have found an x that is epsilon optimal, we can just look at x and figure out all the bits of z. So if you found an epsilon optimal point, you have learned all of z. Unfortunately, we can only learn on expectation 2 bits of z per query. That means that we actually need n by 2 queries. Well, not n by 2, but omega n queries if you use the Markov box. Yeah, and since epsilon was set to be 0.9 by square root n, this is a class of functions which actually requires omega 1 by epsilon square queries in order to optimize. Okay, so that's it for the classical part. We've shown gradient descent supremacy in the classical side, and next I will be moving to quantum. So if there are any questions before that, I will take them now. Cool. All right. So what happened after that? We found out that reality actually is quantum. And what does that mean? So there were some experiments mostly related to light, which had very non-intuitive outcomes. And to explain this, people came up with a new model of reality. And I'm just going to mention the main points of. Important thing is that a particle can be in a superposition of multiple states. So this electron, you would have heard, it could be in a superposition of having gone through the left slit or through the right slit. And this I'm going to write like this. So there's some coefficient along with the state left slit, plus there's some coefficient along with the state right slit. These coefficients are just complex numbers, and they satisfy this equality. They're absolute value squared. If you sum them up, you get 1. And the significance of alpha and beta here, one of their significances is that if you asked which slit did it go through, if you try to detect which slit it went through, with probability mod alpha square, you would get left slit. With probability mod beta square, you would get right slit. A very weird thing, but it's something we've learned to accept if we want to work in quantum computing. Now, what happens to this? So if we let it actually go, say we say, okay, you're in a superposition of the left slit and right slit. Now what's going to happen to the superposition as the electron continues moving towards the screen? Well, it's actually quite simple. So if the left slit, if it had gone just through the left slit, let's call the state that it would have reached at the screen the left spread. So the left spread is it's again some superposition over different locations on the screen. So the electron, if it had gone through the left slit, its position at the screen would have been a superposition of various locations, each with their own complex coefficients. And similarly, if it had gone through the right slit, you would have gotten a similar but slightly different spread on the screen. Now, what happens if the superposition goes to the screen? It's very simple. It's all just linear algebra from this point onwards. The state will actually be alpha times whatever left slit would have become plus beta times whatever right slit would have become. So it becomes alpha times left spread plus beta times right spread. And since left spread included points here and right spread also included points here, the coefficients are going to add up. So if you take some point over here, in this experiment, and if that coefficient is I really don't know anything about quantum mechanics, but this is what quantum computing looks like, which is why I decided to anyway go ahead with this analogy. So let's take this idea and just apply it to quantum computers. If you take a classical computer with, say, b bits of memory, its memory is in one of 2 to the b states. But if you try to make this a quantum computer, the same memory is now, it's in a superposition of these 2 to the b states. And very similar to left slit and right slit earlier, we're going to write it in this way. So this is the state of the memory, and it's a summation over all the possible 2 to the b different base states. Each one has their own coefficients. And it has the property, these coefficients are complex numbers, and they have the property that if you sum up their absolute value squared, or their modulus squared, you get 1. Yeah, so very similar to left slit, right slit. Now, a more succinct way to write this, so if you notice, if you ask what is the state of your memory, instead of actually giving you this expression with a summation, all that you needed to give me were these coefficients. What is the coefficient corresponding to each of the 2 to the b different states? So another way to write the same state would just be as a vector, as a complex vector with 2 to the b different components, and with the property that its norm is equal to 1. So that's all that a memory is in a quantum computer. It's literally just a vector. Now, in classical computers, we can apply AND gates and OR gates and stuff like that to our memory. What can we do in a quantum computer? And this is, so all this is really actually similar to probabilistic computing up to this point. The place where it really changes is in the operations that we can perform. And one obvious thing that operations must have is that they have to preserve norms, because a state has to have norm 1. So after you've done the operation, the resulting state should also have norm 1, because that's the only way in which it's a valid state of the memory. So we want certain types of operations such that no matter what vector is fed into that operation, the output vector should also have norm 1. And it should also be a linear operation, because that's how the left spread and right spread worked. And a nice linear algebraic way of characterizing this, the only linear algebraic stuff that you can do that preserve norms are to apply a unitary m. So you have a vector phi, you apply a unitary m, the new state that you get is m phi. So what this means, if you unpack the definition of what a unitary matrix is that each of these base states actually has to get mapped to a valid superposition. So if you just look at what does the state m map to, this must map to some vector phi m which also has norm 1. And additionally, each of these mappings, so if you look at phi m1 and phi m2, where m1 and m2 were different base states, these two states must be orthogonal to each other. And this is an equivalent statement. You can either say you're applying a unitary matrix M, or you can say you're mapping your base states to vectors in such a way that all the resultant vectors have to be orthonormal to each other. And another way of phrasing this is that you're changing the basis. You started off with some vector phi, you've changed the basis, and when you look at the same vector from this new basis, you have some other vector psi, I think, yeah. And and these alpha m's are now given by the entries of psi instead of phi. So it's a very weird thing that we can do, but it's also where quantum computing gets its power from, the fact that you can just change the basis. And so this results in very nice tricks. So if you look at Fourier transforms, they're also just doing a change of basis to a different orthonormal state. And this is something that quantum computers have used to huge advantage. If you want to know how does factoring work, it actually just does a Fourier transform. And there are various different algorithms that use Fourier transforms in various fields. So what is a Fourier transform? It's just a simple fact that these vectors over here are all orthonormal to each other. So omega here is the nth root of unity, which means that if you look at the complex numbers, if this over here is 1, then there's some complex number here which is called omega, in which this angle is 2 pi by n. And it has this nice property that if you take omega square, it just nicely goes around the circle until you actually get 1 is equal to omega to the n. Okay. Now, I actually introduced this because I was planning to show a surprising quantum algorithm. I don't know if I have time for it. Okay, I actually might skip the quantum algorithm, but I'll just tell you what it does. So suppose you're trying to you're given access to a function f, which is...
Sorry, Suhail. You can go up till 6:15 easily. We started late, so yeah.
6:15, sure. Okay. I think I'll still have to rush it, but...
Okay, yeah, sure. Your call. I'll just letting you know.
Yeah, thanks. Okay. So for those who haven't seen quantum computing yet, this will be your first taste of quantum computing. It might look a bit scary, but it's just that it's very hard to write down. Logically, it's quite understandable things that are happening. So let's start with a function here, which just takes two inputs, say x and y, and it outputs a real number. And you would, in a quantum computer, what you would try to do is you would create some kind of state. So over here, this over here is saying, I've created the state where, yeah, so I'm querying the points x1, y1, x2, y2, and so on. And I'm putting my state in a superposition of these. So it's also in the state x1, y1, it's also in the state x2, y2, along with some appropriate coefficients. And if I make a query with the state in mind, I will also get the values of x1, y1, along with x1, y1, along with x2, y2, I will get the values fx2, y2. So it's kind of, you've created a superposition of what query you're going to make, and then you make the query, and so your outputs, it's kind of like you've also found out all the outputs in parallel, but they are still in the superposition with the same coefficients. Because that's how quantum works. Each basis state here will, each basis state here is going to proceed as if there were no other states. So it would get fx1, y1. This basis state will get fx2, y2. And then you do the same linear combination that you had started with. So you get the same coefficients. All right, so this is what an example state looks like. And what I'm going to describe now, yeah? Yes, that's a good question. Yes, because there are actually infinitely many inputs that you could have. So I actually don't want you to think about the discretization because it will eventually not be relevant. So as far as this is going to be a high-level thing that we're doing right now. So if you could just think of it as actual inputs, that would be much more convenient for the both of us. So anyway, this was just an example state that I put here. Now let's assume that our function f was, as we had seen at the very beginning, let's assume our function f is just our inputs x comma y, inner product with some vector v. So over here v is the vector a comma b, and f of x comma y is just equal to v inner product x y. So what I'm doing over here is I'm trying to look for a quantum algorithm that is actually computing the gradient. And I'm not going to go through each step. I don't have the time for that. But what you can do is you can query at a grid of points. So I'm querying at x1, y1, x1, y2, x1, y3, and so on. I'm querying at a complete grid of points in superposition. So that's why x over here takes all the possible values of x, y takes all the possible values of y, and together they take all possible values of xi, yj. If I make the query, I will get xi, yj, and the place where the quantum f of xi, yj, and I can I've added the coefficient omega to the f. Does basically is if your value is increasing a lot. So if you look at, say, f is steep in the x direction, then if you look at the various values here, you will be getting omega to the
Suhail,
yeah.
Sorry, there is in the chat asking they got lost at the graph. Could you explain that graph
sure.
again?
So this is a 2D plane. I have the x-axis here and the y-axis here. And I'm just marking a grid of points here. So there's the point x1, y1, x1, y2, x1, y3, so on till x1, yn, and so on x2, y1, x2, y2, x2, y3. I've selected a, and I'm making my quantum computer create a superposition of all these points. It will be querying all of these points in superposition. That's all that this was meant to indicate.
Hope that is.
And once it makes the query here, along with xi, yj, it gets the value of f of xi, yj. And the next step that we do is we take f of xi, yj, and we put it over here. We in some sense, we put it into the phase. Okay. So if f is actually steep in the x direction, then so the coefficient of x1, y1 will be omega to the some value. So you have x1, y1 along with some coefficient of omega. You will have x1, x2, y1 will also have some coefficient of omega, but this will be much larger than this because f is steep in the x direction. So as we move from x1 to x2, f of xi, yj is increasing fast. So this coefficient, so this exponent of omega is also increasing quite fast. That's the idea behind this. And why do we want to do such a thing? It's because all of these vectors were orthonormal to each other. In this, the exponent of omega is always 0. There's omega to the 0, omega to the 0, all the way down. In this, it's increasing very slowly, just by 1 each time. Here, it's increasing by 2 each time, by 3 each time, and so on. Right? So when we do this calculation, we have that the coefficients of omega are increasing by exactly as much as f is steep in the x direction. Okay. And I'll probably send these slides if you're interested in seeing how the calculations work out. But what you finally get is this. You'll finally get a state which is summation omega to the something depending on a, where a is this value over here. This is telling you how steep you are in the x direction, and that's also reflecting over here in how fast the exponent is increasing. And similarly here, we have b is how fast you're increasing in the y direction, and it appears here to show you how fast the exponent of omega is increasing. I can't take questions on this because it will take too long to actually flesh out all the details. But now all that I want to do is a change of basis. Because if I now change the basis based on those orthonormal vectors that I showed earlier, this state over here, it was some state of the form 1 by square root n times 1 omega to the some aib, sorry, what? an by 3 omega to the 2an by 3 omega to the 3an by 3 and so on. So this was literally the an by 3th element of that set of orthonormal vectors. Right? So if I change basis to the basis of orthonormal vectors, this is just going to become 0, 0, 0, so on, and 1 at the an by 3th position, which is brilliant because here, if you look at this state and you try to measure the state, we would have gotten this top, and you would have gotten any of these values with equal probability. But now by changing the basis, you're always going to get an by 3 if you measure. And that's in part how quantum computers do their magic. So if you change the basis here, and then you change the basis for yi, you can literally, from your state, you can read out the values of a. And this wasn't actually restricted by only being in 2 dimensions. If I had taken f to be an n-dimensional function, it still holds the same. With just 2 queries, I can find out what the gradient is, or, well, not exactly, but to any epsilon that I want, to within any margin that I want, I can find out the gradient with just 2 queries. And so it definitely does help in computing gradients. If you're given Oracle access and you're not given, and you can't use the cheap gradient principle, then this does help in computing gradients. Of course, that seems like a bit of a detour because what we want to know is, given the gradient oracle, what can it do? So that's what we're going to do now. We're going to give quantum computers the gradient oracle as well. So that kind of cancels out this advantage that it had. And we're asking, does it have any extra advantage in actually doing gradient descent? Yeah. So now let's get to the same function class that we had earlier with the various +1s and -1s. If you try to prove that you actually need omega n queries even for a quantum computer, you will reach a roadblock because this is actually possible in square root n queries. So the counterexample that we had, or the lower bound that we had in the randomized case, does not work in the quantum case anymore. And the reason behind it is, again, another fabulous quantum algorithm, but I can't get into it. There's something called Belove's algorithm. It also has some fascinating tidbits. For instance, we know that Belove's algorithm exists because of some nice mathematical characterization of quantum algorithms, but we don't actually know of a way to implement it. So we know that there is an algorithm, but nobody can ever use this algorithm until we actually find out how to implement it. Okay. So now this brings up the question, what is the state of gradient descent for quantum? So we know from a recent paper that there is an omega 1 by epsilon lower bound, which kicks in when n is equal to 1 by epsilon square. So this means that perhaps quantum can actually solve the task of convex optimization with 1 by epsilon queries, but there's no dimension independent algorithm that does better than 1 by epsilon queries. And our main contribution in our paper was to show that, in fact, it needs 1 by epsilon square queries. There is a family of functions for which it actually requires 1 by epsilon square queries. The unsatisfactory part about it is that it kicks in only for functions of this larger dimension. So in fact, right, so what are all the lower bounds? If I had to draw it here, so here we have a lower bound of needing omega square root n log 1 by log 1 over epsilon queries. This is too cluttered. In this region, we have a lower bound of omega 1 by square root n. And eventually, over here, if you do 1 by square root n, that's the same as 1 by epsilon square. From this point onwards, we know that we need 1 by epsilon square queries. So the upper bounds and lower bounds do not match before 1 by epsilon to the 4. They only match afterwards. Now, in the next few minutes, I will attempt to walk you through the quantum lower bound, the main ideas behind it. Right, so here the question about discretization. So your input could have been any value from r to the n, but obviously that's not practical, so we're going to work with some discretization of r to the n. And similarly, the output space, the function value and subgradient values will also have to be discretized. But it turns out that it doesn't matter what discretization we choose. So we're going to let the algorithm designer choose what discretization they want. And regardless of which discretization they chose, we'll show the same lower bound of omega 1 by epsilon square. Right, so ignore this line here. So what we're going to ask from the oracle is basically this thing, that if x input that we're querying, and f prime are two different functions which behave exactly the same at x. So f of x is equal to f prime x, and the returned by f prime at x. Then we insist that the output states should be the same whether we were querying f or whether we were querying f prime. As long as our input is x, it doesn't matter whether we're querying f or f prime, the output should be the same. That's the only restriction we ask of the algorithm designer. Okay. It makes clear sense in classical, but things get a bit messy in quantum. So the base function we actually take from another paper that had come out a few years earlier. They had shown lower bound in a very interesting model where you have a randomized algorithm, but you can make parallel queries. And they had shown some lower bound there, and it had the nice properties that we needed for quantum. And so we ported the same lower bound to quantum. And the base function might seem a bit weird at first. So if you can see, the function takes in an n tuple. So it's in n dimensions, the function. But it's only returning the maximum among the first k dimensions, x1 till xk. We actually don't care about the remaining dimensions. And the first dimension has a slight advantage above the second dimension, because this is x1, this is x2 minus gamma. So x2 has to be at least gamma more than x1 in order to be the maximum. So x1 has an advantage in being the maximum here, and so on. The advantage goes through all the coordinates. And we'll think that gamma is small, so it's not much of an advantage. So because gamma is small, the minimum is still going to be something like minus 1 by square root k. And the point at which it achieves this will be something like minus 1 by root k for the first k coordinates and 0 afterwards. And this is the base function. We're going to again create a function class from this base function. For creating this function class, we're going to need k orthonormal vectors in R to the n. And this is what our function class looks like. Given k orthonormal vectors, we're not taking the maximum of x1. Rather, we're taking the maximum of v1 inner product x, and v2 inner product x minus gamma, v3 inner product x minus 2 gamma, and so on. So if you think about this, this is like you're viewing x from the basis defined by these k orthonormal vectors. So the function's properties shouldn't change that much. It's just a change of basis. So its minimum is still going to be minus 1 by root k, and it'll take that value at around that, at a easy to compute point. Again, we set epsilon to be 9 by square root k. Again, this means that if x is epsilon optimal, then f of x should be minus 0.1 by square root n. Right. Now let's analyze the behavior of f here. So let's assume for now that the queries we're making are of norm 1, norm at most 1, and v1 till vk are sampled uniformly at random. So then it doesn't matter which x you choose, since v1 to vk are chosen uniformly at random, x is going to look like this. v1 inner product x. In fact, all of these inner product, all of these different components are going to be really small. They'll be within, say, log n by square root n and negative log n by square root n. This is a fact that we had seen at the beginning of this lecture as well. And we're going to use this. So we're going to keep n really large so that these components are actually really small. And we'll keep n so large that even gamma is going to be large compared to 1 by square root n. Remember that gamma was something that we had considered to be small. N is going to be large enough so that even gamma looks large. Now, this is the idea behind the lower bound is actually pretty simple. V1 inner product x is going to be the maximum. I'm going to claim that this is with high probability going to be the maximum. And that's because all of these values are between 1 by root n and minus 1 by root n. And every subsequent value takes a hit of at least gamma. So V1 inner product x, we can just think of that as approximately 0. V2 inner product x minus gamma is approximately minus gamma. This is approximately minus 2 gamma, and so on. So the output from this is going to be V1 inner product x. And the gradient is going to be, the subgradient that we get would just be V1. So we've gotten V1. We know that V2 through Vk have to be orthogonal to V1. But we know slightly more than that. We know, for instance, that V2 does not belong to the set of vectors such that V inner product x was, say, greater than gamma, 2 gamma. Right? So if V inner product x, if V2 inner product x was greater than 2 gamma, which would happen by fluke, because that's extremely unlikely, then we know that the maximum would have been V2 inner product x and not V1 inner product x. So we don't just know that V2 through Vk are orthogonal to V1, we do know something slightly more. And that is going to be annoying. Because if we didn't know anything more, if we just knew that they were orthogonal, then we could have continued the same story. After the first query, we know what V1 is, so we can set this value to whatever we want by choosing an appropriate x. But if we actually didn't know anything about V2 through Vk, then this is still going to be just 0 minus gamma. So this is minus gamma, this is minus 2 gamma, this is minus 3 gamma, and the maximum would have been the second coordinate. And so the second query would have revealed. And again, if we didn't know anything else about V3 to Vk, our third query would have revealed V3, and so on. After k minus 1 queries, Vk will still be nearly at random from a large dimensional space. So this is still going to be close to 0. And remember that for an epsilon optimal point, it's necessary that Vk inner product x should be something like minus 0.1 by square root k. And this is way too close to 0 for it to be epsilon optimal. So that's the lower bound idea. In each query, we're forced to just get one answer at a time. And so we need k queries in order to find out Vk and finally set an answer such that Vk inner product x is minus 0.1 by square root k. Of course, as I said, there are annoying points that it's not actually truly at random, it's only nearly at random. And another annoying point is that this is fine for a randomized lower bound, but we want to do a quantum lower bound. And so how do we make this a quantum lower bound? I'm out of time, so I won't go into much detail about how we do this nearly at random part. But I'll get into why this is hard for quantum as well in just a few minutes. All right. This goes via something called the hybrid argument, which is very useful in cryptography and quantum. We start off by creating our first query. It can be a superposition over many, many different points. So I'm just going to write it like this. We're querying x1, we're querying x2, and all these things in superposition. When you ask the oracle to give you the answers, you're going to get something like this. So along with x1, the answer changed this phi1 in some way to get psi1. So psi1 is somehow representing the answer of f of x1 and the gradient. And so this is what's going to look like. However, instead of passing it through this oracle, you can also pass it through this restricted oracle, which just answers the value of v1 inner product x. Now, since we know that v1 inner product x is anyway with high probability the actual answer of fv of x, right? So we had with high probability, the first query that you make is actually just going to be v1 inner product x. This really doesn't change the answer much. So for most of these values of x, it's going to be the same answer. For some values of x with extremely small, for an extremely small fraction of the x's, the answer would have actually changed because it should have given you v2 inner product x minus gamma, but instead it's always only giving you v1 inner product x. So the answer is slightly different from what it should be. And so if you look at what the original was, you had this original answer and you have this corrupted answer. Now all your operations after this, they're all unitary operations because that's all that quantum can do. And unitary operations always preserve the norm. So if you look at how this algorithm proceeds from the original state and from the corrupted state, so original, say this output was v, and in the corrupted one, the output was, not v, let's call it phi. Let's say this was phi and this was phi prime. We know that phi and phi prime are actually really close to each other. At the end of the algorithm, you will have the state m phi, where m is some unitary or product of unitaries. And here you have m phi prime. And unitaries preserve distances. That means that m phi is also close to m phi prime. So the fact that you've only changed a small fraction of the superposition will actually go all the way through, and it will say that our final state and end are also really close to each other. And so our final output of the algorithm itself has to be close to each other. And that is the weakness of quantum algorithms, that they can only do unitary operations. So if you've hardly made any difference at the beginning, it cannot blow up at the end. All right. Another benefit to making this corrupted state is that this state is actually independent of x2 till xk. So earlier we were saying that x2 till xk are nearly at random. Now they actually are truly at random because this state only depended on v1 and it didn't depend at all on v2. And so the way this argument will go is that we just corrupt it over and over. In the second query, you would have gotten the output in some way. Instead of actually giving you this oracle and this answers, I'll give you the answer of v1 inner product x and v2 inner product x minus gamma. We know with high probability in our second query, this answer is the same as fv of x. Maybe there's a slight, some small locations where it changes, but again, that's just with really small probability. And so we do this k minus 1 times, and we have and therefore doesn't really make much of a change to the algorithm. And if you've corrupted it k minus 1 times, that means that the state at the end of that doesn't even look at vk. None of the oracle answers involved vk at all. So this actually is independent of vk, and when it tries to output something, it has to fail because it doesn't have any information about what vk was. And because the k minus 1 times corrupted algorithm fails, so should the original algorithm also fail. That is a very rushed but accurate description of our lower bound. We actually had to modify it a bit for queries which are larger than 1 norm. And the dimension that you get if you run through this argument is 1 by epsilon to the 6. we brought it down to 1 by epsilon to the 4 using some modifications from the same paper that we borrowed the function from. Yeah, actually, I'll move over to open questions now. Yeah, that's all for the talk before the open questions. So for those who are familiar with gradient descent and its variants, gradient descent worked when our function wasn't changing too fast. It was one Lipschitz. Suppose you have a function which isn't just Lipschitz, but its slope itself doesn't change too fast. So notice that for our function, which say maximum of x and minus x, that is a V shape. So although the function doesn't change too fast, its slope changes from 1 to -1 all of a sudden. And if you're guaranteed that that doesn't happen, then the optimal algorithm is something called accelerated gradient descent. And it manages 1 by square root epsilon steps with that guarantee. And it's optimal for randomized algorithms. And we also showed that even for quantum, accelerated gradient descent is the best algorithm. The open problems are of a similar nature. What if we change the guarantees that are given to us? What if our function that we're trying to optimize is not just convex, but say it's a quadratic function? So in that case, we don't know whether quantum computers can give a speed up over classical computers or not. Those are the more high-level open questions. The more low-level open questions directly related to this talk is, what is the complexity when n is smaller than 1 by epsilon to the 4? We haven't settled what the quantum complexity of convex optimization is. We saw that the class that we used for the randomized algorithm actually got a quantum speedup, and that's what people are more interested in when there actually are speedups. So what other classes do get quantum speedups? It's an interesting question. And this question is, and it was my favorite after I tried it for a while and gave up. I think I'll still go back to it at some point. This doesn't have the minus gamma and minus 2 gamma and so on. What is the quantum complexity of optimizing this function class? So if it turns out that this requires omega n queries, that will settle the first question. Sorry, omega k queries, that will settle the first question. If it's actually faster, then that gives you something for the second question. I'm sorry, I had to rush it a bit at the end there, but I was taking way too long.
Thank you. It's all good. It's nice talk. So let me start with a quick question then. So are the V's known in the last this FPX V1, V2?
So this one again, V1 till Vk are the hidden.
Hidden. These are the ones that, okay.
They're just some orthonormal vectors.
Any questions for Suhail? We have a couple of more minutes. Any comments? Maybe I will ask one. Why do you need to go to the higher dimensions? Where does it become useful? Like, where does it forces you to go to the higher dimensions?
Oh, thank you. So, okay. So, yeah, it'll all be there right here. Okay. So we know that Vk inner product x is going to be something like 1 by square root n. Right, so everything here is, and we want to make sure that if this is 1 by square root n, it's not small enough. So suppose it was actually minus 1 by square root n minus k times gamma. We want this to be larger than minus 0.1 by square root n.
Right.
And the other constraint that we want is that gamma, we said gamma is small, but it's large compared to 1 by square root n. So we want gamma to be greater than 1 by square root n. And you combine these two, and it will say that n has to be at least 1 by epsilon to the 6. Sorry, this is k.
we have a somewhat, I don't know, do you want to take this, since you are starting up on quantum, there is a question is like, if a student want to start learning about quantum computing basics, where do he or she should start?
I mean, there are various ways you can go about it. I suppose you could start with textbooks, and textbooks do give you a nice intro to things. Of course, a course will help you answer your doubts live, unlike a textbook. But another nice way of doing it is just, you learn the very basics of quantum computing, then you read up on some quantum work, and whatever you need to learn to understand that quantum work, then you learn on the fly. You just keep on referencing something for that. That's my preferred way of learning these things. The famous textbook is Nielsen and Chuang, which is very widely.
Okay, I have a question.
Yes.
Yeah. So, I mean, at least like from an overview point of view, like throughout the beginning of the talk, I was assuming that you had proved a bound for the time complexity for gradient descent of any general function, but then somewhere in the middle you picked a class of functions, and do you prove a bound just for that class, or does that help you prove for anything?
I see. No. So whenever we choose a class of functions and prove a lower bound, it's specifically for that class. It does have nice implications. So I think the way to look at this is that when we started off, we had this actually quite nice proof over here that gradient descent will only take 1 by epsilon square steps. In 1 by epsilon square steps, you will always reach an epsilon optimal point. So this is true for any function. And you might ask, okay, if this is true for any function, is there another algorithm which does better than this, which is also true for any function? And that is what our lower bound is against. So suppose there was a statement saying for all f, you need only, say, 1 by epsilon queries. So the negation of this would be just there exists an f such that you need more than 1 by epsilon queries. So our lower bound is to be thought of as really against these kind of statements that are general and not, well, I guess, well, there's a difference. So this is a statement against general algorithms, and to refute it, you only need a specific function. So we don't have a statement for generic functions, but we have a statement against generic algorithms. Yeah.
Right. Okay. Fine. Nice. Okay. Yeah. So no one can give a general.
That should not be possible, and you can have some trivial functions, which I guess you can't have a lower bound against.
Okay, so that is why in the last slide as an open question you say what is the quantum complexity for that other class of functions, because that could be better. That could be better. Okay, fine.
And that would be
so like it could be that like loads of other classes of functions have better complexity. So I mean, it's not hopeless or anything.
It's not hopeless. It's not at all hopeless. For instance, we already saw a class that did get a square root speed up.
Right. Yeah. Okay.
Yeah.
Nice. Also, I just want to confirm if, I'm sure I'm messing up the details, but I want to confirm if I got the overview of your idea of proving the lower bound correct. So you said instead of the oracle that's giving you the actual values of the function, you have this faulty oracle that keeps giving you the wrong values.
Yes.
And now you run some quantum algorithm and it definitely has to be wrong. And you say that since this wrong oracle is only slightly wrong, the answer can only be slightly different from the original, if it were giving you the original oracle. And so it has to fail for even if you give you the...
That's exactly the idea. That's the idea behind what's called the hybrid argument. And it looks like cheating the first time you see it, and even like every time you see it, it's cheating. But it works. It's a beautiful argument because, so the previous paper over here, and so everyone I think who's taking this lecture at least, if you hadn't heard of the hybrid argument before, it's very useful. So I mentioned that previously there was a lower bound against randomized algorithms, which have some kind of parallel query, and that we were using the same function. So they were also proving the same lower bound, but they instead decided to quantify exactly what nearly at random meant. We used the hybrid argument because we wanted nearly at random to be truly at random. And when we chose these cheating functions, these cheating oracles, they actually would be truly at random after that oracle call. So we completely circumvented the need to quantify nearly at random by choosing the hybrid argument. And if you actually choose the other way of quantifying nearly at random, it gets quite messy. So another contribution, which we don't state because that is really weird to state, is that we've simplified these people's proof by using the hybrid argument instead of their in-depth analysis.
Okay. Where did I missed the problem, I missed the part where nearly at random comes up at all.
I see. So that was here. So when you query the first vector, we said that V1 has to be the output. And with high probability, V1 will be the output. And you'd want to say, I got V1, and I haven't learned anything about the other VIs. Because, so this statement, the statement that V inner product X, this value is at most 1 by square root n or something like this. If you take a random vector V, then the fact that this is small, this is only true when your V is actually random. It's uniformly at random. And you would guess that if V is also at random, you get some similar statement, maybe with 0.9 or nearly uniformly at random. If it's not nearly uniformly, it's possible that you can find an X for which this value is actually large. Like if you know V, if V is not random at all, then you can actually make this as large as 1. I always say that V is actually at random. And the argument that we'd want to say is that in our first query, we learned V1 because this has to be the maximum. And the others are still at random, completely at random. The problem is that that's not true. The fact that you got V1 as the answer does give you some information about V2. It tells you that you didn't get lucky and get V2 as the answer. So V2 is not one of those lucky vectors. So it does leak some information. So we can't actually say that V2 is at random after the first query. But if you use a cheating oracle, which only gives you the answer of this, then we can actually say V2 is random because V2 was not involved at all.
Oh, okay, I see. Okay, yeah. Also, yeah, the other algorithm that you mentioned for like using the Fourier transform to compute the gradient descent. Yeah, that was very nice. Yeah, this is the first time I've seen something like that. Yeah, thanks. Yeah, enjoy the talk. Thank you very much.
Glad that somebody understood something from that part. I had to rest that a lot. Yeah, that's fine.
We can, yeah, probably put it in the, yeah, let's share it. It's actually a chat. Go ahead.
Don't forget to like, comment, and subscribe.
Yeah, thanks. Yeah.
Great. So shall we wrap this up? Any more questions?
Hello, I have one question.
Yeah, sure.
Yeah, I did not listen to your talk fully. So,
Okay.
so what would be the sequel to this in a stochastic setting? So instead of full gradients, as you know, in
Right.
machine learning, we are used to stochastic gradient descents. So what are your ideas on sequel to this proof in those?
Yeah, I guess, so one advantage with gradient descent is that the guarantees that it gave were very nice and it gave us a nice problem to attack. I don't I've seen some works on stochastic gradient descent in order to see how this should be extended, but I'm afraid I couldn't find a nice problem to latch onto over there. So
it's certainly going to be a bit more complicated, I guess, because of these partial gradients, and you have to see things in expectance and so on. So, yeah.
So there have been some works on computing the mean value of vectors. So suppose you have an oracle that's giving you vectors, and you're trying to estimate just what is the average of these vectors. There has been some work on this in quantum, and that seems to be relevant for finding out just what stochastic gradients are. But yeah, I didn't. It's just this high-level connection that I noticed. I didn't see anything more deep. In some sense, this isn't really. This is more about convex optimization rather than gradient descent in particular. Probably didn't need to. Yeah, but this is the, I guess, the main headline of this. So I think the main question we need in order to port this to something related to stochastic gradient descent is what is